Hello everyone, welcome back. In this lesson we are going to be spending some time looking at angles of elevation and angles of depression. We have two objectives, and those are to define and use the terms elevation and depression, and to use trigonometric ratios to calculate angles and lengths. So let's begin by talking about what we mean by angle of elevation and angle of depression. Let's imagine for a moment how we normally see things. So let's do a quick sketch. Let's say this is the diagram of an eye, and that's our pupil. We normally see in straight lines. We kind of impossible to see around corners, so we see in straight lines. So here we go, and this line of sight is what we call our normal line of sight. Going to leave it there as normal. Now sometimes we may need to look at something above or below, and usually we turn our heads, or sometimes we rotate our eyes, and in doing that we create angles. So if this is our normal line of sight, which is straight ahead, and let me just write that, straight ahead, and then we look upward at something, then we create an angle right here, which is what we call our angle of elevation here. So we are looking, this is our normal, this is where we are, this is our normal, so we rotate our eyes upward, and so this becomes our angle of elevation because we're looking up. And from the same point, if you need to look downward at something, then the angle that's formed on this side becomes the angle of depression. So in this diagram we see that if the person is here and looking out, this is a normal, and once you're looking out that way and then you need to look downward at something, then the angle of depression is formed here. And depression in the sense that you're looking down at something and not feeling sad. So it's not a sad angle, it's just that we're looking down at something. And so here we have our angle of depression. Now notice here that we have a line that is also parallel to the other line here at the base. So this line is parallel to this line, and because of that we actually find that this creates a alternate angle. So a pair of alternate angles, so one there and one here. And from what we remember, alternate angles are equal to each other. That is important to point out now, because they come up later on in our working out of questions. Angles of while working with angles of depression and sometimes elevation, we often come across Z angles or alternate angles, and alternate angles are equal to each other. So let's jump into some questions and see how we can work them out. Of course, in working out questions in elevation and depression, we're going to be using trigonometric ratios, which are sine, cosine, and tangent. Now, a man on top of a lighthouse sights a boat at an angle of depression of 25 degrees. So man up here looking out, and this is the angle of depression of 25 degrees out to the boat. The distance from the man to the boat, that is along this line, along the line of sight, is 52 meters. How far away is the boat from the foot of the lighthouse? Now this is the lighthouse. This is the lighthouse here. And we want to find the distance from the boat to the foot of the lighthouse. So we want this angle here. Now, as we discussed earlier, the angle of these two angles are alternate to each other. And so this depression angle of 25 degrees, we can actually write it here as an angle of elevation. It becomes 25 degrees just the same. They are equal to each other. And now we have a triangle which has an angle inside it, and we have a distance on it. Of course, we could use this as well. We could say, okay, this is 90 degrees, and from that 90 we can take 25, and this would leave us with 65, and so we'd have another angle in there. We could also use that approach. I'm just going to use this one that says this angle is that angle and work it from there. So we have this number, which is for this triangle, the hypotenuse, and we want this side, which is the adjacent and hypotenuse together That gives us the cosine ratio. So we can say the cos of 25 is equal to d, which is the adjacent side, divided by 52. And a simple cross multiplication here. 52 cos 25 gives us d. And once you punch that into your calculator, remember to put your calculator in degree mode. We end up with 47.13. Of course, the question is going to ask us to correct it to the nearest meter, and therefore d is equal to 47 meters. So that's this question. Moving on to another one. Here we have a similar another question. Here we have two buildings are 45 meters apart. From one window, in one of them, the angle of depression of a window in the other building is 17.6 degrees. How far below the first window is the second window? So let's just put a little bit of context here. Let's say we have there's a building. Not that it's important to draw this, just adding some context to the question. So here's a building, here's a building. All right, sketching it out. All right, so there's one building, there's another building. There's a window here on this building, and there's a window here on that building. And what we want to find is the distance between the two windows, which is this distance here. Now, based on what we talked about with the alternate angles, this 17.6 is exactly the same size as this. And so we have a triangle now where we have an angle inside it that we can use. We have 45 degrees, and we want to find this side. Now this side is the opposite, and this one is the adjacent. Now opposite and adjacent gives us tangent, and so we can say the tangent of 17.6 is equal to the opposite side, which is h, divided by 45. And doing a simple cross multiplication again, we have that 45 tan 17.6 is equal to h, and punching that into our calculator gives us 14.3 meters. Now writing this to two significant figures. Remember, you start counting significant figures at the front of the number. So we start here, 1, 2, and then decide what to do with the next number. If it was 5 or more, we add 1 to that. Since it's not 5, we just ignore it and just write our answer here as 14 meters. And so that would be the distance, the height difference between the two windows, first window and second window. Moving on to another question. This is from CXC. In the diagram below, not drawn to scale, RST is a horizontal straight line. So RST is horizontal, and UR is a vertical pole. That's important. So horizontal and vertical, we end up with a right angle there. And we have some numbers. ST is 15. So ST is 15. So this is 15 meters. And these angles are given. UST is 120 and STU is 40 degrees. Those are there. So we are to find first the angle of elevation of U from S. So U measured from S. So we are at S. So this is where we are. And so what we want to find is our angle right here. Now notice that this angle along with this one creates a straight angle. And straight angles, as you probably remember, measure 180 degrees. So this angle here, RSU, is what we want to find. And RSU is going to be equal to 180. 180 is the entire straight angle, minus 120, which is this side of it. And we end up with 60 degrees for that answer. So this answer here is 60 degrees, and 60 degrees is the angle of elevation of U measured from S. All right, now that we've done that, let's move on to finding the length of UT. UT is this side, and we don't have many other measurements to find it. We have a measurement on this triangle, so let us separate this triangle a little bit. Let's draw it out here, draw it a little smaller for space reasons. Alright, so let's fill in what we know about that triangle. This angle here is 120. This angle here is 40. And we know that angles in a triangle, when you add them up, they measure 180 degrees. So 120 plus 40, that's 160. And so this angle here would be 20 degrees. And we also know that this side is 15. Now, in terms of using sine and cosine and tangent, we can't use any of those because this triangle that we just drew, this one right here, is not a right angle triangle. So we have to use another tool, and looking at it, since we want to find UT, this is U, this is T, and this is S, we have to use what we use the sine rule. So the sine rule says now that the side, the length of the side divided by the sine of the angle is equal to any other side divided by the sine of the angle. So let's write it down. UT over sine 120 is going to be equal to 15 divided by sine 20. I'm doing a bit of cross multiplication here. UT sine 20 is equal to 15 sine 120, and so UT, therefore, doing a bit of division here, is going to be equal to 15 sine 120 divided both sides by sine 20 over sine 20. And so once you type that up and you put that in your calculator, you're going to end up with 17.98 which is roughly 18 meters. So this side is 18 meters. And so we have found our UT, and now we need to find the length of RU. Now RU is the vertical, vertical line, the vertical pole. So we want to be working with this triangle. Now let's work with this triangle here. So I'm going to draw that triangle there and extend outwards. We have just found the outside line, so we have just found 18, and we want RU, and this is here is T, so we have to draw the big triangle and put in the 40 degree there, and of course our right angle here. Now since we want RU, notice going across here, this is the opposite side, and this side here is the hypotenuse. Opposite and hypotenuse, that's sine, so we're going to be using the sine ratio there. So the sine ratio says that sine of 40 is going to be equal to opposite, which is RU, divided by 18, and we can do a simple cross multiplication there again. 18 sine 40 should give us RU, and of course you plug that into your calculator, 18 sine 40, and that is equal to 11.57 meters. So we have found our lengths. We have found UT using the sine rule that gave us 18 meters, and we have found RU, which measures 11.57 meters using the sine ratio. Let's look at another one, also from CXC. Let's see if we can make this thing a little bigger. All right, that should help. And so here we have a diagram. In the diagram below, not drawn to scale, GH is a vertical pole. It's 12 meters long. Standing on a horizontal plane. This is a plane in place, that is a flat line, flat place. H, J, and K are in a straight line there. And we have some numbers. As we said, we have GH is 12, and now we have J the angle of elevation of the top of the pole G from J and K are 32 and 27. Now the question is, where do you put these two numbers? Notice something, that if you stand here at K, for example, let's say you're standing here at K and you walk toward the base of the pole, and as you go closer to it, then it's going to be a little harder to see the top of it, and that is because the closer you go toward it, the angle of elevation becomes bigger and bigger. So this line, as you keep going closer and closer to it, the angle of elevation becomes bigger and bigger. And so the idea then is that because the closer you go toward it, the bigger the angle gets. It means that the bigger angle is supposed to go here, that's 32, and the smaller angle goes further away or furthest away, that's 27, in case you had more. And so we have put in our diagrams the angles of elevation, and let's put in our right angle here because this is a vertical plane, a horizontal plane, that's a vertical line, so you have a right angle there. And we are to do some calculations. We are to calculate the length of HJ. HJ, now where is HJ? HJ is the base of this triangle right here. So let's just cut out that triangle and draw it. And this is all kind of emphasize how much this is useful to separate the diagrams when you're looking at them. So this is G, this is H, this is J, and that angle there is 32. And we want to find HJ here. Now opposite, adjacent, that's tangent. So we say the tangent of the angle, which is 32, is equal to 12 divided by HJ, opposite over adjacent. Do a cross multiplication here and we see that HJ times tan 32 is equal to 12, and dividing both sides by tan 32 we end up with HJ is equal to 12 divided by tan 32. We can plug this into our calculator. 12 divided by tan 32 is 19.2. It's meters, so yes, let's just write that, 19.2 meters. And that's that one. Then we need to find JK now, and JK is this piece right here. So to find JK, what we can do is to find this entire length here. We can say HK, let's just write that out. HK, as this entire line, is made up of these two pieces, HJ and JK. And so if we found HK, we can do a subtraction by saying JK is equal to HK minus HJ. We already found HJ, it's 19.2. So all that we need to do then is to find HK, and the HK is in the bigger triangle. So we can just draw that triangle, the bigger one. And that angle there is 27, and our right angle, and this is 12. This is G, this is K, and this is H. So we want to find this side, HK, again, opposite adjacent, that's tangent. So we say the tangent of 27 is equal to 12 divided by HK. No, it's going to be the same workout as this, as you probably realize. So we can say HK is equal to 12 divided by tan 27. And plugging that into your calculator gives us 23.6. Take some time to stop and check it before you move on. So we end up with 23.6 here. And so now that we have our number, all that we need to do is just to subtract it. So subtracting here, we have JK would be equal to 23.6 minus 19.2, and doing the subtraction there, we end up with 4.4 meters, and that would be the length of this part. So by separating the triangles and looking at the diagram, we realize that if we found this long piece and subtract this shorter piece, we'd get that one. So sometimes it's useful to write out an equation, in simple equation there to show the lengths, and that will help you decide what you need to find. And having done that, we can find our missing piece, our unknown piece, that is. Moving on to our next question, we have a diagram not drawn to scale again, and the diagram not drawn to scale shows a vertical tower FT. So this is FT, and then on top of it is an antenna TW mounted on top of the tower. A point P is on the same horizontal ground as F, so these are important, same flat line, such as PF is equal to 28. PF is equal to 28. Let's just write that in. PF is 28 meters, and the angles of elevation of T and W, that's these, from P are 40 and 54. So again, using the same idea that if you should go closer to the base of the tower, then the angle of elevation gets bigger, and you go further away, it's smaller. So we're going to start off by using this one as the smaller of the two angles. So this is 40. Now if you raise your eyes to go upward, it means that you'll be making the angle bigger, which means that this angle from this line to this line is where your 54 is going to go. So from here to here is your 54, and from here to here, from this line to this line, is your 40. And now that we have done that, it says put in the distance, put in the angles and any right angles. This is a flat plane, this is a vertical tower, so naturally here is a right angle. And what do we need to do now? We need to calculate the length of antenna TW using the same thing we did a while ago, with the idea that this long one, FW, is made up of FT, which is the tower, and TW, which is the antenna. That if we do that, we will realize that TW, the antenna, is equal to FW minus FT. And so that's all we need to do. We need to find FT and we need to find FW, do a subtraction, and we're good. And we will find the height of the antenna. So let's draw our first diagram. Let's take out this diagram here, this triangle here, and have a look at it. So here we have 28, we have 40, and this is our TFP. Now we want to find FT. So look at it here. This is opposite, straight across from the angle, that is adjacent, and that's telling us that we must use tangent. So the tangent of 40 is equal to FT or TF over 28. This one is simple. We can simply cross multiply that. 28 tan 40 gives us FT, and so 28 tan 40 gives us 23.5. That's that. And then we can find the other one now, FW, by drawing the bigger triangle. So let's draw the bigger triangle. So this is 54. That's our right angle there. And this is F, this is W, and this is P. Of course, this is still 28. And we want to find FW. So using the same idea, tangent of 54 is equal to opposite FW divided by 28. Cross multiplying again, 28 tan 54 gives us FW, and punching that into your calculator gives 38.5 meters. And so now all that we need to do is go ahead and subtract them. So the antenna would be equal to FW minus FT, which is 38.5 minus 23.5, and that gives us 15 meters. So the height of the antenna here is 15 meters. 38.5 minus 23.5. And so these are common questions that come up on your CXC paper that you should be familiar with in terms of elevation and depression. It's a very useful application of trigonometric ratios, and it's a useful thing to learn. It's also very interesting because it comes up in other things later on if you do engineering and things like that. So that's it for now. I hope that this lesson would have made the concepts of elevation and depression angles clearer to you, and you can find more practice and past papers on the website at csecmathtutor.com. If you are new to the channel, please remember to subscribe before you go, and thank you very much for watching. Continue to working hard. Best wishes for your examination.